Okay, hello everyone. Welcome to the fourth session of our quantum computing workshop, QSilver36. And we can start. Przemek, the Zoom is yours.
Okay, thanks, Paweł. So, can you hear me, or should I do something with my mic? Because
I can hear you.
okay, very good. Okay, so hi everyone. So during the last lecture, we discussed quantum Fourier transform and quantum phase estimation algorithm. And as far as I remember, we didn't code much when it comes to quantum phase estimation. So today we will start by doing some coding exercises with about QPE. And then we will move on to the next topic, which is order finding algorithm, which is basically the core of the Shor's algorithm. And as we discuss the order finding algorithm in theory, then we will also move on to some coding exercises. And after today's lecture, there will be a coding assignment for you. So today there will be no quiz, there will be only, I would say, a pretty long coding assignment to do. And during the next lecture, so tomorrow, we will discuss the short code, and I will also, and it will then become clear for you why we are learning all of those algorithms. Yes, because you learned already about QFT, which is used in quantum phase estimation, which is then used in order finding algorithm, which is used in Shor's algorithm. Yes, so there is like a very clear path of things to learn. Okay, so let's move to quantum phase estimation. So a quick reminder: in quantum phase estimation, we have two registers. So here, this register, yes, this at the bottom, is the state vector register. It's called in this way. And here, and this vector, this state, yes, this register is something that is already given. So this is an input to QPE. This operator U is its general form. It's also given. And this state, yes, here, the vector that represents the state is an eigenvector of this operator U. And we want to find the eigenvalue. And here we have another register. So this is, I believe, in the notebooks called the first register, and I like to call it the eigenvalue register, when we will try to encode the missing eigenvalue. And the first important thing to remember is the amount of qubits in this register when we have all of those x's depends on our choice. So the more qubits we put in here, the bigger the register, the more accurate our result should be. Because, let's me scroll, for example, down, yes, if you have some unknown eigenvalue, and this eigenvalue is for us unknown, and using QPE, we want to express it in binary form, yes, and there usually there will be some estimation error, yes, because it's quantum phase estimation, and here we will have some estimation error, and this error will become the lower, the more qubits we have. So, for example, if I have 1 or 2 qubits, like I can land pretty distant from the true value. But if I have like dozens of qubits, then I will be more accurate, yes? And the true value will become will be unknown to me. But of course, if you are able to calculate it precisely, which you can also do on paper, yes, but if you have a very complex matrix, very big matrix, then this is a tedious task. But as if you can calculate the real value, then you can also calculate the estimation error, yes? So this is also a nice task, like to ask yourself, like if you have some eigenvalue that you know the value of, then try to guess what will be the range of our estimate, depending on the size of this register. Okay, and now about the algorithm itself, so the process. So here to the eigenvalue register, we apply Hadamard gates all the way. And then we apply this operator which is given here, yes? And the control qubit, there will be also only one, there will be only one control qubit at each time, will be each of those qubits in the eigenvalue register, yes? So those dots that you can see here. And here we have u to the power of something, yes? So here we have u to the power of 1. So this is basically a controlled u gate, and u gate, as I said, is given. So here we just apply a simple controlled u gate. Then onto this, using the second to last qubit from this register, we apply u squared. Then if we have here like the third qubit, then we would apply controlled u to the power of 4, then controlled u to the power of 8 gate, and so on and so on. So as I remember correctly, I believe yes. Here, like I was talking about it, yes, so we have this u squared, u to the power of 4, u to the power of 8, and so on and so on, and then 16, 32, and so on and so on, yes? So here is the notation of this. And at the very end, we need to apply inverse Fourier transform. Here you can see the dagger, which means that here we have a Hermitian conjugate, and a Hermitian conjugate of quantum Fourier transform is equal to the inverse quantum Fourier transform, yes? Because this is one of the properties of Hermitian matrices, and quantum gates are Hermitian matrices, yes? So you can inverse a quantum operator using a Hermitian conjugate. And then we measure it, yes? And this way we would obtain the angle of rotation. And as we know the angle of rotation, we can calculate the eigenvalue itself. Okay, so now let's move on to the task. Here we have some, as the input, we get some unitary operator u with eigenvector ket1 and eigenvalue e to the power of 2 times pi times I times p, where p is given. And as you should remember, we have controlled z power gate. Here the phase is given. So here we use this controlled z power gate, where we get put in the exponent 2 times phi, yes? So this is because we have phase is equal to p, so 5 divided by 16, and times 2 because here we have 2. So this is like given to us, yes? And we simply need to write it, but in another terms. So another thing to remember from this task is that if you have the eigenvalue, you can very easily construct this unitary operator, yes? So let's run this code. Okay, and here we have the number t, and t in this notation, yes, as you can see, is the number of qubits in the eigenvalue register. So it will determine the precision of our computation. And here we are told that to pick t equal to 4 and write a function, write a code to apply quantum phase estimation, yes? And some technical hints. What should be an input? So here T, so the accuracy. Control qubits, which will be qubits in this register. Then we have the target, so target qubits or target register, which should be also given. And circuit object and operator CU, which we just create. We also have a note that we will get an exact result since we have like an easy problem. So here t equal to 4 will be precise. And this is easy to guess that this will be enough because here we are, as you can see, divided by 16, yes? So 2 to the power of 4. And I believe that usually, like if you have some real world examples, like this number will not look so nice. But here we have like this introductory task. So let's proceed. Here we have some hints again that we can use powers, and for IQ of t. We have written, yes, this is already here given for us. And maybe a small, and this is like nicely here wrote, and maybe a small thing to remember. So inverse quantum Fourier transform, apply the quantum Fourier transform, but in reverse order. So we start with swap gate, then we apply those CR gates, so controlled rotation gates. It's in this part. And then we apply the Hadamard gate, yes? So we are doing the same, but in reverse order. And then comes the meat and potatoes. So here we have QPE function to write, yes? So first we are told to apply Hadamard to control qubits. So here we will refer to our circuit object and use append methods. And then we need Hadamard operator. So it will be circ.Hadamard. And now if we want to apply Hadamard on each of the qubits from the control register, we can use here on each. And then we want to apply it to control register to control qubits. Okay. Now it should be okay. Then we need to apply the CU gates. So the one, so we will be basing on the gate that we already have created. So this will be given, and depending on the qubit that will be the control qubit, we also need to adjust the power we will be raising our gate to, yes? So since we need to apply this gate over all the control qubits, I will write a loop. So for I in range, and here the number of qubits in our control register, so our precision T. And now we need to create a matrix, so create an operator of suitable power. So I would call it CUI, and as you probably already read, we can use exponentiation of matrices, like there was a thing above. And here we basically need to write like this formula, yes? So there we have like 2 to the power of t minus 1. But here I can write 2 to the power of I. And why? Because I here, like this range, will span from 0 to t minus 1. And as you can see here, those exponents also span from 0 to t minus 1. So actually, we don't need to put any minus 1 here, since the span of this range will do this for us. Yes. Okay, and then we need to apply this gate that we just created. So circuit append, and we want to apply this gate. And then here we need to first of all define the control qubit, and this time it will be only a one control qubit. So it will be from control register, which I just wrote, and then we need to specify which qubit, and it will be t minus I minus 1. And this is because like for I equal to 0, yes, we need to start from the furthest qubit. So if I is equal to 0, then this qubit will be the qubit number t minus 1. So let's move back. It will be this qubit. Like yes. Okay, and then we need to choose the target. So here you also need to remember that about how the range is closed and open. Yes, in Python, range is always open. And target, so we want to apply this on all the qubits in the target register, so in the eigenvector register. And then we need, so here we have this loop, so we apply those CU gates over and over. And then we need to apply the inverse quantum Fourier transform. And here we can use this function. So IQFT. And here the first argument is the number of qubits. And here, as you can see, it's equal to t, yes, because we want to apply the Fourier transform all over of those qubits, and that is t of them. And maybe a remark about the numbering, like in the code, we started from 0 and we ended at t minus 1, yes, so this is why we have t minus 1 here. So IQFT, and here we have t qubits. And we also need to pass on which qubit, so how the register is named, and it's named control. Yes, like we have here this control register, we need to pass it here, and the name of a circuit, which is that circuit. Okay, and okay, I had an indentation error. Okay. So we have the QPE. So now we want to create like the whole circuit. So here we are initializing the circuit. Here we want to set N and T. So T, as we already did this, is equal to 4. And N, in our case, will be equal only to 1. So N is the size of an eigenvector register. So the size of this register. And since, as you can see, we have the unitary operator with eigenvector ket1, then it means that our register, eigenvector register, will have only one qubit, yes? Because it would have like 2 qubits. Here we would need an eigenvector that would have 4 elements, and ket1 have 2 elements. And if eigenvector would have 8 elements, then we would have n equal to 3. So 3 qubits in a target register, yes, and so on and so on. So we can deduct the number of qubits in a target register just by looking at the size of an eigenvector of our operator. And so this is n equal to 1. Now we need to create those registers. So let's start by creating the control register. So our accuracy. Here I will make a list of those qubits. I use line qubit to create them. And here I will use a list comprehension to make it work faster. Yeah, this is more of an optimization thing, yes. However, if you come back to the notebooks from the first 2 days, like there were other methods from creating a control register. This is only one of them. And then we need a target register, which we already said there was only a single qubit, but to be consistent with the notation, I would like it like that, or maybe like that. Why? Because we want a proper numbering of them, yes? So here in the control registers, we would have qubits numbered from 0 to 3, because here the range like is open. And then here we will have a qubit number 4. Yes, so this is like to keep the numbering of qubits in place. And then we need to set target qubit to store eigenvector. So we need to prepare our input state. And as we have read in the task, the eigenvector is equal to ket1. And since our qubit is initialized in the state ket0, so the qubit is in our target register, then we need to convert it to ket1 simply by using xgate. Yes, so circuit append x, maybe to make it clear on each target. Okay, then we can apply the QPE, and this should be pretty easy since we already wrote a function for it. And here we need to pass t, so the accuracy of our computation, the name of a control qubit, control register, which is as control, similarly the name of the target register, and then the general formula for our operator. So CU. Okay, and then we are told to measure it, and okay, I believe it's already written here, yes. So we append the measure function where we want to measure the control register. We want the result. So let's check if I have any or name error. X is not defined. Okay, so I believe I need to import the xgate from circ, which will be from circ import x. CEO of one position, target. Okay. I forgot about the circuits, yes, because we have 5 arguments to pass. Okay, now this should work, or maybe not. Hmm. Then inside we have this append. t minus I minus 1. If anybody see what's wrong, please text me so it will be a little bit faster. Because I think it's some stupid mistake. Like really easy thing, like base times 2. Okay, here it is okay. See you. Minus 1. Save it. Okay, range T. Control T. So let me check it. Okay. Here, yes. This was, yes, so now it works. Yes, so here I forgot that if I want the numbering, like in the control, I would have the number 1, 0, 2, 3. Maybe I will comment it. Yes, and here I just wanted to have the number 4. But by writing this in that way, I accidentally got something like this, yes. So I got those like this like repeated, yes. And I didn't want it. I only wanted the fourth qubit, so I needed to start from there. So that was the mistake, yes. So okay, and that's it. Also, somebody wrote about the control. Let me check. I believe it should be the same, but yes. So like applying this asterisk, like in this case, wasn't important because the on each method can deal with that, but this is not universal, and I believe this is still a good remark. Yes, to remember about this thing. Okay. So here we received the result, and we need to convert it to binary form, yes. And here we have 1, 0, 0, so I will copy it. Yes, maybe here. Oh. And how to decode it. So we have 1, 0, 0, 0, and here you need to okay, so like wrong notation, I'm mistaken with Qiskit. So here we get the result of 5 that was repeated 1,000 times. And this is because like we get an exact result, yes? So here you can see this note that t equal to 4 is precise enough. So here we receive like basically a deterministic result, which is equal to 5. And since we have 4 qubits, it's like 5 divided by 16. So we need to convert it to binary, and then we would get this result. So we get 5, yes, as we could have seen. And since we are using 4 qubits, then we need to divide it by 2 to the power of 4, so we get 16. Yes, so this is, we obtain an angle of our global phase in the quantum phase estimation. Okay. So now let me check if I have something else interesting in this task. So in the next task, you have basically the same thing to do, but for different fee, for the different phase. Yes. So here we would see like different estimations. And okay, and here is this situation where I say that this target register will have 2 qubits because the eigenvector of U operator of which we want to find the phase has an eigenvector with 4 elements, so 2 qubits required. Yes, and here you have like this task in, I would say, true setting where p is unknown to us. Yes, and here you are asked to try different t values, but this is mainly like the of how accurate you would be. Yes, so I believe that like you can try 3 t equal to 3, then to 6, and so on. So and after some point, adding another t, so adding another qubit to control register won't change anything. Okay, so now let's move to the topic of the day. So order finding algorithm. I will switch here. So okay, so now get rid of that. So I will make a very brief introduction to RSA encryption and shorts algorithm. Tomorrow I will talk more about this. So in RSA encryption, we have 2 prime numbers. Let's call them P and Q. And if we multiply them, we get a number, let's call it big N. And in this encryption, N is a public information, yes? Or a public key. So it's public and it is not known to us. And to bridge the code, to bridge the encryption, we need to guess P and Q. Basically, if we guess one of them, then guessing the other one is pretty trivial. For example, if you guess P, then Q will be equal to N divided by P. But this is only like a side note. And in general, if you are given only N, finding P and Q is extremely hard task. But someone it was known from, I believe, like 18th century, figured out, and this is thanks to Euler's algorithm, Euler's theorem. Euler's theorem in number theory, yeah, like because there are many Euler's theorem that states, in our case, that if we raise some number which is co-prime with our big N, yes, here is small n. So co-prime, it means that it does not share any divisors, yes? So the greatest common divisor is equal to 1. And if we raise this number alpha to some power, eventually we will get a remainder of 1 when divided by n. So let's write it down. Okay, maybe I will call this just number a here. And let's call this exponent r. And now let's introduce this modulo n. And do not mistake it with modulus, which we talked about during the first lesson. Sorry, with modulo, because this is modulus, yes? So the remainder, yes? Modulo or remainder. I will rather use the word remainder, yes? So for example, if you have like 8 mod 3, 8, oh sorry, 3 modulo 8, it tells you that after dividing by 8, the remainder will be equal to 3. So for example, such a number will be like 11, yes, so 11, so if you divide 11 by 8, you will get a remainder of 3. And so on and so on, yes, and if you also divide, let's say, 19 by 8, you will also get a remainder of 3. So this is our operator, and someone has spotted us like those two formulas are pretty, let's say, they're pretty close to them when it comes to finding those two factors. However, the problem is it is still extremely hard to find this R. And today we will learn how to find this R, and tomorrow I will tell you how to, from the information about R, get the information about P and Q. So how to find those factors and defactorize the number n, and then break and decipher the RSA encryption. Yes. Okay. So so to make it clear, yes, this theorem states that for any n, there exists such a that is co-prime with n, then exists an R which for which this equation is true. And in our algorithm, we will pick A randomly. It will be just our choice. Yes, and then if we pick a number that is co-prime with this big N, then we are guaranteed that there exists such R that meets this condition. Yes, that meets this equation. Okay, so now let me give you an example. So yes, let me open a spreadsheet. And here, let's say that we have two prime numbers, P and Q, and P is equal to 11 and Q is equal to 5. There our N, so our public key, is equal to 5 times 11. Yes, so it's equal to 55. And now let me rewrite this formula. A to the power of R is equal to 1 modulo N. So now let me make some lucky guess about A, and it will be always a lucky guess. So let's say that A is equal to 3. Yes, I will say I chose it randomly. And now let's make a table where I will test different R's. So those different exponents. So here I will have the exponent, also known R, and the remainder. So remainder, or maybe not, the remainder will be there. So maybe I will call it modulo. And here the result of exponentiation of exponentiation. Okay, so here let's say that we have 0, 1, 2, 3, 4, and so on. Maybe I will, for now it will be okay. And now the result of exponentiation, so a to the power of r. So it will be a to the power of r. And here I need to log the cell, okay. So here you can see that we have 1 because 3 to the power of 0 is equal to 1, like everything that is to the power of 0. Here we have 3 to the power of 1, which is equal to 3. Then we have 3 to the power of 2, which gives us 9. Then we have 3 to the power of 3, which gives 27. And 3 to the power of 4, which gives us 81. And now let's calculate the modulus. I will use here a function that we already have in Excel, yes. So it will be this number and this number, and this one I believe should be log. Yes. So if we divide 1 by 55, we will get a remainder of 1. Then 3 divided by 55, we will get a remainder of 3, and so on and so on. Here we have a number 81, which is the first of those numbers bigger than 55. And if we divide it by 55, we will get a remainder of 26. So far, except from 0, none of those numbers meet this equation, yes? So now let's make this table a little bit longer. So as you can see, those numbers are getting big pretty quickly, despite we started from number 3. Okay, so as you can see, I've calculated here the remainder for different R's. And here you can see that it gets bigger, then it gets smaller, bigger, and so on and so on. So here you can see like a real pattern. But here is the thing that we are looking for, and we will use an order finding algorithm to look for it. And here we have, of course, a pretty easy example, yes, but in real world applications, this n will be like equal, like we have even thousands of numbers, yes, not like 2 numbers. So here is an R that meets our expectations. Let's make it bold. But another thing to see is that this pattern starts to repeat, yes? So here you have 1, 3, 9, 27, 26, 23. And here again, you have 1, 3, 9, 27, 26, 23. And this is pretty important for us, yes? Because like the fact that you can change the problem of finding P and Q into the problem of finding R, like it was already pretty early. But Peter Shor found out that as you keep raising this R to higher numbers, so getting a higher exponent, and then calculating this remainder, you can see that the pattern repeats. And if you come back to the previous lesson when we were talking about the discrete Fourier transform, you should have remembered that we were talking about converting number of occurrences to frequencies and vice versa, yes? So frequencies to numbers and from number to frequencies. Now, the order finding algorithm utilizes the Fourier transform to find R, and it will become extremely important for us. Another way to think about it is that, well, in quantum computing, we pretty often dealt with like going in circles. Yes, like you have e to the power of I times something, and if this something was too big, you would make a full circle, and very often the pattern will repeat. So here we have a very similar pattern. When if we keep going enough, then we will start from the beginning. Okay. Okay. So now let's come back. Okay, so let's say that we have an operator U that performs modular exponentiation. Yes, I will say what this is in a minute. Performs modular exponentiation. Yes, and sometimes it's also called modular multiplication. Why? Because why exponentiation or multiplication? Because we are raising to even higher powers, yes? And then we are getting this mod operator. So we have here a matrix, a quantum operator that both at the same moment performs this exponentiation and calculates the remainder. And how this operator is built is beyond the scope of our course. So it will be just given to you, yes? And I believe that in our notebooks, I will show you like it's given. There was, I believe it was this operator. Yes, yes. So we will just load it. It's given to you, yes? You don't need to construct it by yourself. Like nobody expects this from you. And okay, so we are given this, yes? So you don't need to worry about this. So in other words, if you have some state vector y and you act with this gate on it, then you will get the following result. N, where this y is actually, this one, yes, is a number between 0 and n minus 1. And if n, this big N, yes, can be written using n bits in binary, then quantum state Y requires n qubits. Okay? So the size of this register, of this, the register that Y represents, will be equal to log, the logarithm of base 2 n of n, yes, but we need like to round it up, always up, to express a number that is big enough, yes, but we will come to that later during the coding session. We will do it automatically, of course. So let's now repeatedly apply U. So let's say that our vector is just cat1 to just make it simple, yes? Just for example, yes? Example. So let's say that this number represents our R, and we will try to guess what happened. So following this formula, we get here a to the power of 0, and here I have forgotten about our state. So here we get a to the power of 0 times 1, because this is our state, yes, it's equal to get 1. And here the remainder operator from n, yes, so here nothing changes. And of course, this is like equal to 1 mod n. But this is a trivial example. Now let's apply this with the first power. So our R is equal to 1. And if you apply it here, then we will get a to the first power, yes, times 1 mod n. And let's make one more example. So u to the second power, it will be just a to the second power times 1, remainder n. So now let's move on to some R. And R, as by definition, will give us a remainder of 1 when divided by n. So let's write it initially in a long way. So this one. And now we can also write it as 1 remainder of n, yes. So after some times, if we raise it to some power r, we will get to the state where the remainder will be equal to 1, which we can also write in that way, yes. So a to the power of 0 remainder of n. And this will be like useful later on when we will be proving why we should use quantum phase estimation to make this algorithm work. Okay. Sorry, I had the wrong thing. Okay. Okay, so now let's prepare some state. And now I will try to, given this modular exponentiation matrix, I will try to show you how to derive its eigenvector, yes? Because we say that eigenvector is given to the quantum phase estimation algorithm. So we need to know how to construct it, yes, first of all. If we are already given this modular exponentiation operator, then at least we can try to derive its eigenvector. Okay, so first of all, I will show you how this eigenvector looks, and then I will show you that this is exactly an eigenvector. So first of all, consider of superposition of all of those states that we wrote here. Yes, so a to the power of 0 times 1, remainder of n, then another state a to the first power, a to the second power, and at the very end a to the nth power times 1, remainder of n. And let's give them coefficients that will look as follows. So e to the power of minus 2 pi I, some number S. And this all divided by R, where S will be equal, will be an integer that will take values from 0 to R minus 1. And so I write it maybe this way here, like for the first element. So I would like first coefficient. So our eigen vector, let's go with the little index s, will be equal to. So first of all, we need to divide it by the square root of r, which will, why r? Because that's how many states we have, so how many qubits, and then write the individual states of those qubits with their coefficients. So the coefficient for the first qubit will be equal to e to the power of minus 2 pi I, this s value, divided by r times, and then this vector, yes. So a to the power of 0 remainder of n. So here we have our first qubit, then another qubit will be a bit similar, so minus 2 pi I, here as 1, and that all, this exponent divided by r, and here a 1 remainder of n. Yes, and so on and so on. And our last qubit will have a coefficient of e to the power of I minus 2 pi I times, here it will be s of r minus 1, and this all divided by r, and the qubit itself, a to the power of r minus 1, remainder of n. Yes. So here is this value like expressed in binary, so using up to n qubits. And okay, let's close the parentheses, and then let's write it in a shorter way. So we have here this r, so we know that we have an equal superposition thanks to this. Let's write a sum sign, and let's use an index k ranging from 0 to r minus 1, where we can simply now write, okay, where we can simply write e to the power of 2 pi I s k divided by r, and this state k modulo n. So now let's show that this is our eigenvector. So for that, we need to find out that this is that after doing this multiplication as the output, we will get again this vector times some scalar which modulus is equal to 1. Okay, so now let's write it down. So we have our Vs vector. Here we have this summation sign, r minus 1 minus 1 I s k divided by, okay, it's all divided by r. And now let's apply this u operator So we can take it like inside this summation. And let's use it here, yes. So modulus of n. So in this line, we put this U matrix inside like the parentheses, or in this case, the summation sign, yes. So we basically moved it here, and we also expressed this vector in a longer way, in an elaborate way. So now, as a next step, I will rewrite the coefficient R, and now maybe I will expand this sum. So here you will have a parenthesis, and we will have those coefficients 2 pi I s. Here is 0, like for the first element. And then, of course, we have this gate, and a times 0 to the power of 0, remainder n. And then here we need to expand the sum to the last element, yes. So if the power of minus 2 pi I s, here it will be r minus 1, I believe, yes, r minus 1 divided by r. Apply the U gate and write this coefficient r minus 1. Yes, because we have to r minus 1. Okay. So now let's see what will happen if we finally apply this U gate to our vectors, to our qubits. So again, we have our initial coefficients for the equal superposition, and now the coefficients will not change. So it will be still e to the power of minus 2 pi I s 0 times k divided by r. And here, by definition, like of this U operator, here, U to the first power, we know that it will basically raise this power of A by 1. So in other words, if you apply this to A, let's call this exponent M, remainder of N, yes, it will give us a the power of N plus 1 modulus N, which you can see here on the left, and we will use it below. And so here, for the first element, we will get A to the first power, because we have like a 0, so now we have 1, and the remainder. And now let me like skip those less important ones, and let's move on to the last element, 2 by I s. Here we gonna get r minus 1 again. Divided by r. Sorry, like this, okay, shouldn't be there. And this, yes, so we have a to the power of r minus 1, so now we will have a to the power of r. N. And now, a very important thing, we noticed that if we have here a to the power of r, this is equivalent to a to the power of 0, yes? like by the by definition of R. Like we know that here we have 1. So this is also 1 modulus n, yes. And now, if you like forget about the coefficients for a moment, you will see that nothing has changed, yes? So here we have qubits from a to the power of 0 to a to the power of r minus 1, like this like span of exponents. And here again, we have a to the power of 0, then we have a to the power of 1, and then it will all range to the a to the power of r minus 1, yes? So somewhere here, there will be r minus 1. So once we have like reached the a to the earth power, we can start again from the number 0. So if we forget about the coefficients, we will get again the state vector Vs, which is an eigenvector. And now, if we multiply this result of this multiplication by, I will write it in that way. If we multiply it by e to the power of 2 raised to the power of 2 pi I sum s divided by r, and again by e to the power of minus 2 pi I s divided by r. And as you can see, this is like if you combine those two values from the exponents, if you add them up, which you can do when multiplying the exponents that have the same basis, they will cancel out and they will be equal to 0. So this is like e to the power of 0, which is equal to 1. Yes, but expressing this in that way, it will make it obvious that we will obtain here and e to the power of 2 pi I times s divided by r, and then this equals superposition, so r, and then inside the parentheses we have e to the power of minus 2 pi I s of, and this time of r divided by r, and 0th power remainder of n. Yes, and here we have this r, because here we have 0, but since we multiplied it by this number, yes, so it went here, and this went here. So it changed in that way, yeah. And for like other states, we will get a similar result. So maybe now let's move on to the last element. So we will have e to the power of e minus 2 pi I s, and here we had r minus 1. So now we can write it in this way, yes. So here you also need to remember about like this thing that we spotted, yes. So then it will become, I believe, clear why we express it in that way. A r minus 1 mod n, yes. So now what we have just discovered is that here we have this Vs, and here we have an eigenvalue. Okay? So since Vs is an eigenvector of U, we can use the phase estimation algorithm to estimate this eigenvalue. Yes, so here we will use the QPE to find this. Yes, because here we have some S and R. And so here you can see that we have two unknown variables to guess, S divided by R. And we will also learn how what is this S, like basically it's like another pretty hard part of the problem that you need to spot that that you needed another variable to introduce. And there would be an algorithm, a continued fraction algorithm to deal with it, but this will be a classical. Okay, so we need to work. So first of all, the controlled U gate. So this modular multiplication is given to us. And the second thing is the preparation of an eigenvector of U. So here I gave you the mathematical formula for that. But we also need to prepare it, yes? Maybe I will check the chat. Okay. Okay, so to prepare Vs, so our eigenvector, we will begin by considering a following superposition. So again, follow an equal superposition depending on the value of S. Yes. So here we have this. So here we have this S number, yes. And now it will change value from 0 to R. So we will have an equal superposition of different states with different values of S, which is one of our unknown variables. And just broader picture to notice is that we will use the superposition in the phase estimation algorithm. And since the eigenvalue of Vs is equal to that, the phase estimation algorithm will yield an approximation to this, yes? And but it will get an approximation only for one of those S, where S can be, as I already wrote, can be equal to 0, 1, and so on, until we reach R minus 1. And the bad news is that we don't know which S it will use, which S will be used to yield an approximation of S divided by R. So each of those S can be chosen at random with the probability of 1 divided by R, yes, because here we have R elements. And okay, so now let's consider this superposition of states. Okay. And let me show how to construct it. So let's rewrite the first term. And now let's rewrite also the sum sign from 0 to R. And now let's expand the definition of Vs. So it was 1 divided by square root of r times the sum from k equal to 0 to r minus 1. Here should be plus or minus 1. And then this coefficient minus 2 pi I s divided by r. And then the number, like some number expressed in binary. And this we can rewrite as 1 divided by r times the summation from k equal to 0 to r minus 1. Then again summation, so we have here put this 1 divided by square root of r before the summation. So now we have two summations, and here we will have s from 0 to r minus 1. So we have also changed the orders of those summations, and here we will have our coefficient, so minus 2 pi I s k divided by r. Yes, and this multiplied by ak, remainder of n. And now, if you think about this expression, or maybe even broader about this expression, yes, about the whole summation, if k, so here this k is equal to 0, so the first term, this whole exponent is also 0. So here every element in this summation is equal to 1 because we have e to the power of 0. So if k is equal to 0, then we have e to the power of 0, which is equal to 1. Then this summation, I will call it this way, yes, will be equal to r, because here we have r ones from s to 0 to r minus 1. There are r elements, and each of those elements is equal to 1. So this summation is equal to r if k is equal to 0, and if k is not equal to 0, this whole summation is equal to 0. But let me show you why. So let me define small omega, which is equal to e to the power of 2 pi I about s now. So just ik. So here's pi I k, yes. So now this term in parentheses becomes from s equal to 0 to r minus 1. We have here omega to the power of s, yes, because here we skipped s, oh, here should also be r, sorry, yes, we have small omega to the power of s. And this we can rewrite as, for s equal to 0, we have 1. For s equal to 1, we have just omega. Then we have omega squared, and so on, until you get omega to the power of r minus 1. And if you look at this, yes, this is a geometric series. Yes, so here we have a summation where we multiply, where we have the elements that are multiplied by omega one after another. So let's call this sum S. So this series, let's call it S. And as you maybe know, there is a formula for calculating this summation. Yes, this the value of this series, and it looks as follows. Yes, so like this is like I will not like this formula is pretty easy to derive. Like you basically need to raise it summation to the second power and then calculate s minus omega times s, and it will give you the thing that we have here in the upper part. Yes, so if we now plug in the definition of omega, we will get 1 minus e to the power of minus 2 pi I s k, and yes, and maybe times r divided by r, yes, so it will be equal to 1. And here we will get 1 minus e to the power of minus 2 pi I sk divided by r, and here we get 1 minus 1 because here we have uh, r divided by r is equal to 1, and here we have s time k, which will always be equal to here to 0. Yes, and maybe so why it is equal to 0? Yes, because here we have 2 pi, yes, and you should know that this part is an integer, so this is like a full circle, yes. So if we have like sk is equal to 1, then it will be just a single full circle. If s times k is equal to 2, it will be another circle, yes? And it cannot be any other because we know that s and k are integers, and we are not dividing by anything here because we have r divided by r, which is equal to 1. Then we know that we are taking the full circles. So this expression and this exponent will be equal to 0 or minus 2 pi or minus 4 pi, minus 6 pi, minus 8 pi, and so on and so on. So anything that will be equivalent to the e to the power of 0. And so to continue here, we get again the same expression. So I will maybe just copy it. Yes. Which is equal to 0 because here we have 0. So now we can see that this expression, yes, so I will just like, okay, mark it with an asterisk, is equal to 1 divided by r times r, because we know that this summation is equal to 0 for most cases, but when k is equal to 1, it is equal to r. So we know then that this whole summation, this big one, will be equal to r. So times r, and then we get our qubit. Yes, so mode n, which is in short equal to 1 remainder of n. So as you can see, the equal superposition of eigenstates is precisely equal to this formula, which is easily prepared by starting all qubits in states 0, 0, 0, 0, and 1 at the end. Yes, because we need to express this in binary, which will be 0, 0, 0, blah, 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 and 1. So you will need to initialize a register that will be capable of expressing n minus 1 in binary, and then in that register express just number 1. Yes, so it will be something like that. And here we will have an it will be like log 2 n. and round it up. Okay. Okay, so then let me just go back here. Order finding, yes. Okay, so by using this, so once we have found S divided by R and we prove that this is indeed an eigenvalue, yes, of our operator, our modular exponentiation operator, then we can use the quantum phase algorithm to find the eigenvalue. So in other words, also to find S divided by R. So now, but our goal is to find R, and now we need to use a procedure, a method, and it can be executed classically, called continued fraction. Okay, so now let's suppose maybe that we have from measurements, yes, we measured our result at the end, and our result expressed in a decimal form is equal to this thing, yes? But now, how to get R from such a fraction, yes? So now let's express it in some better form. Yes, divide by 10,000. But this is still not R, because there are many ways to express this fraction to get exactly this number, yes? So we need here a continued fraction algorithm, and the first step here, since S divided by R is less than 1, the first integer that we will use will be equal to 0. So we will need an integer that will give us like the non-remainder value after doing this division, yes? So here we have so this number is smaller than 1, so here is 0, 6, 2, and okay, 10,000. Then we need to invert this fraction, so we will get 0 plus, and here a big line, 1 divided by 10,000 divided by 1,562. And now we can express this as a mixed number, yes? So similarly as it did before, but now it will, I think it will be more clear. So it will be, I have here already calculated it, 6 plus 628 divided by 1,562. Yes? So this thing we expressed in that way, yes? And here again, we are left with some fraction that is less or 1, and here is some integer. And now we repeat the procedure. So we will now obtain again 0 plus big line 1, we will get 6 plus, and then again we need to revert this fraction. So 1, 5, 6, 2. smaller line, 6 to 8. And as you can see in this number, we can fit to 628. So it will become 0 plus big line 1 divided by 6 plus 1 a bit smaller line. Here we will get 2 plus 306 divided by 628, yes. And so on, yes. And eventually, I can, like, we are short on time, so I will not be showing the whole example. We will end with something like this. It will be here 1, here will be 6 plus something. Then again, we will have 2 plus, and here we ended, here we finished, plus something. Yes, here will be 1. Then again, this, like, you need to believe me, there will be plus 1. Divide by again something. Here it will be pretty a big number, 19, plus 1 divided by 8. And okay, so we continue until we get 1 here in the upper part, because we could also just then if you revert it, there will be like 8 plus 0, yes? So here, if you try to continue this algorithm, here you would get again 1 divided by 8, and if you revert it, like, you would get here like something like 8 plus like 0 divided by 0, which is a nonsense, yes? So we just stop here, yes? So if you get a nonsense of 0 divided by 0, it means that you need to take 1 step back and finish your algorithm, yes? And okay, and you can like see that you will get a 0 when you have 1 here before reverting the fraction. So now we can list our continued fraction. I will call this list C, and now I need to rewrite those big integers plus the very last denominator. So it will be 0, 6, 2, 2, 19, and 8. Yeah. Okay. And now the zeroth converged. So the zero, maybe I will call it C0, will be just equal to 0. The first converged will be equal to 0 plus, and then 1 divided by 6, which is just 1 divided by 6. The second convergent will be equal to 0 plus a big line, 1. Here we write 6 plus 1 divided by 2. So this thing, yes. And it will be equal to 6 plus 8. So it will be 2 divided by 13, I believe. And so on, so on. So we can continue with this procedure. And for the fifth convergent, for the most precise convergent, we need to basically calculate this whole fraction, yes? So here to calculate the convergence, we need just to like stop at one of those steps. Okay, so the higher the convergent, the better will be our approximation of the value that we started with, yes? And for our period finding problem, this decimal number that I shown you is a guess for s divided by r, where r is the period of modular exponentiation, and s is an integer. So r, you should also know that r must be less than n. And then by looking at the convergence, the best approximation to S divided by R, such that R is smaller than n, will be 1 divided by 6. And in our case, this big N, it was like I didn't say in this example how big our N was, but I believe it should be, well, maybe it should work like if we have 3, 4, 5, 6. Po trzeciej do szóstej. Okay. So if we know N, which is our public key, then we need to choose such an R that is smaller than N. So to check, so let's say that we guess that we will pick this convergent, C1. So now we can see that here we have S, here we have S, and here we have R. Here we have another S, and here we have another R. So we have different we have different choices for S and R depending on which convergent we stopped. And the bad thing is that we may not be sure like which one we will pick, but let's say that using this algorithm we chose this one, yes, by kind of lucky guess. So now we need to check whether this condition is met. So here we have three, the power of R modulo n, yes. So let's assume that our n is equal to 7. So then we will get 1 no n, yes, because R is equal to 6, and we raise 3 to the 6th power, and divided by 7, we will get a remainder of 1, yes. Oof. And okay. And the efficiency of this algorithm is O, in big O notation, is like O and 3. So this is polynomial, yes? Okay, I will take a sip of water. And now I will move on to the notebook for a moment before we end. I can see a thing. Okay. Okay. So here you have some more theorems about how to choose a good T, so a good accuracy for QPE. And there was an interesting task that I want to show you. Yes, so it was, I believe, the task number 5. So let me go step by step through it. Okay, so task number 5, it should, okay, it's here. So we are given this operator, which we talk about, it is given to us, yes? Let's load it. And it acts as I told you at the beginning of the lecture, yes? Here we have some instruction how to refer to that operator. And here we have our lucky guess, and here it's denoted as X, and I called it A. Yes, so this is like X to the power of r instead of a to the power of r. And our public key here is 20. And okay, here so far, like it don't need to be multiplied by two prime numbers, but tomorrow we will deal only with such tasks. And here we can already load the QPE function, and here the inverse quantum Fourier transform. And what we need is to find the estimate for S and R. We need to declare the sizes of our registers. Okay, so let's move. So first of all, here we are. Okay, we need to find the value of, let's say, L, which will be the size of a register that will be used for accuracy, like based on the theory above. So I will declare it as math will fail, so we will round it up. So first of all, what we need to do is to find how many qubits we need to encode this big N, yes? So as I wrote a few times, we need a second logarithm. I will maybe print it. Probably I need to import math, yes. Import math. Yes, so in our case it's equal to 5, yes, so we have 2 to the power of 5 is equal to 32. So because if we run this up, we get here 4 times 4 dot something. So if we run it up, we get 5. And as choice for t, we have here instruction that's about how to choose an optimal value for t. Yes. So it will be equal to call it num t. It will be equal to 2 times L, which we already calculated, plus 1, plus, and then rounding up function, tail, not log, and base 2 plus. Okay, so this formula is like I didn't explain it during the lecture, but here you have like this how to choose an option and an optimal accuracy of quantum phase estimation. Yes. So of course, the more you have, it should be the better, but we should also care about the computational efficiency. So how much computing power do we use? Because the more qubits we have, the more power do we use. And also you have to be aware that in real world applications, while you do not have many qubits to use, so we need to be careful with resources. So now let's print this number. And here, this E is a small number. In our case, 0.1 will be sufficient. So this is error rate, and it should be equal to, I believe, 5, 13. Okay. And I believe I made a typo somewhere. Okay, here. I forgot about the parentheses. Okay, 40 now. And okay, so we can of course also apply the size of the registers. So now I will just, okay, so we need to deal with different conventions of naming variables. and then I want to initialize our control register. So control, I believe I can just copy it, yeah, because we will be doing this like in the very similar way. Yes. But here, like to be more consistent, to make it easier for us, I will this time add +1, yes. And then I want to change the state of the target register to get1, but in a multi-dimensional, because now we have L equal to 5, not to 1. Circle X. Yes. Okay, now let's create the operator CU that we have. So now our lucky guess of X will be equal to 3. And N is equal to 20, yes. So we derive those two numbers from there, from the task. So this is our lucky guess for A, or in this case X. And here we also have an instruction how to declare our quantum operator, yes, which is given. So I will write it this way. So Ux, X, big N. Okay. So now let's call the phase estimation circuit that we already have. So it will be T control circuit and CU. And like we discussed already at the beginning of the lecture, yes, this QPE. And then we need to measure the control register at the very end, yes, so to get the approximation of S divided by R. So this measurement that I'm writing right now will give us an approximation of S divided by R. So measure, here control, and here say result to make it more readable. Then we need to sample the circuit. So I need also to declare a simulator, circ simulator, and then sample it. So samples, I need to use run method on the simulator, and the circuit that I want to run is the same circuit and the number of repetitions. Repetitions equal to, let's say, 1000. Okay. Let's check the circuit. Oh, I didn't initialize the circuit itself. What a shame. Here, the circuit, yes, it should be okay. CU circuit control circuit. Let me guess, target. Of course, target. Okay, here is something in G show. Okay, I will check what's wrong with this. But here we have the samples, yes. So the value of 0 we get here 279 times. So this is not very interesting because we can do anything with that. Here we get 4056. We get it again about 25% of times. Here another number, yes. So they are all, and this is in general recommended to get the lowest value. Mm, I also wonder what's wrong with this. Um, bar, we have here bar, so maybe it should be, no, it should be a list indeed, I think. It was already written, so I think we need to correct it. So I will need a list comprehension. PLT bar, and then here is something for key in results key is okay. Mm, and here I want the key as a string. And as the second argument of var function, let's call the values. Yeah. No? Okay, now it works perfectly. So here you can see that we have four outputs, each of them with rather equal probability. And of course, we skip the zero and we should rather choose the smallest value. Okay, so I think that's all for today. So I believe today you should like focus on things like coding, first of all, coding, then how to get the number of qubits in each register. Uh, and I believe that should be sufficient like to complete the coding assignment. So tomorrow we will talk more about what to do with this S divided by R, what to do with this R to obtain this P and Q from the very beginning of our lecture, because like we spent about an hour on just getting this R from this expression. So tomorrow we will move on to the Shor's algorithm. And long story short, we will do some pre-processing, then we will do this order finding algorithm, then we will do some post-processing of R, and then we will get the output, yes? So we will decrypt the RSA algorithm. Okay, so thank you for today. Tomorrow, I believe the lecture will be a bit shorter, but I'm not pretty sure of that. So remember about the assignments, about the deadlines, and that's all for today. So thank you.
Great, thank you, Przemek. Let's just see if there are any questions on the chat. No. So thanks everyone, and good luck with all the quizzes and assignments. Remember that if you have any questions, you can just ask your questions on Discord. I'll now stop recording.